Welcome to a new lecture about the role of conformal diagrams in general relativity. Today, we are going to discuss the Penrose diagram of the Reissner Nordström solution. As you probably know, the Reissner Nordström solution represents the gravitational field created by a point particle in general relativity. The line element is given by the following expression. Okay, and well, I'm just going to write also the expression of the electromagnetic Q form, right? And well, Q is the charge parameter. Okay, right. Well, one has to distinguish different cases according to the roots of this expression. Okay, so let me just, well, we need to find the roots of this expression, and the number of roots will give us a classification of the Reissner Nordström solution. Okay, I have to solve the second degree equation. I'm going to write down the solutions for you. And from this expression, you see that the number of real roots will depend on the positivity of this quantity. And in this sense, we distinguish three possibilities. Just forgot to write here the roots. Okay. And then the case in which we don't have real roots. Okay. Right. So for each of these cases, the solution has different global properties, and we will notice that because we will get different Penrose diagrams. Okay, so we need to study each of these cases separately, right? Okay, so okay, let's start with this case. Right, well, obviously we have this relation, and yeah, we need to write the metric in a convenient form. We just have to factorize the polynomial we have solved. Okay, then we can write the Reissner Nordström metric in this form, right? Well, I forgot to mention at the beginning that the Reissner Nordström like element is already written in a coordinate system which is adapted to the spherical symmetry. So we can follow the procedure which was explained in previous lecture, right? And that's what we are going to do in this case. So we only have to take this Lorentzian part and do some transformations on it. So I'm just write separately the Lorentzian part, and we're going to transform this into something which is explicitly conformally flat. And here, well, it's easy to guess the transformation which we need to use. Okay, so we have to use the following transformation. Sorry, there's a square missing here. Maybe I can just write it down below, because otherwise I don't have enough space. Okay, so right. Okay. Okay, and so if we do this transformation, it's we get an expression in which the metric is conformally flat, takes a conformally flat form. Okay, so that's what we get. And now, well, the procedure is pretty much the same as what we did in the Schwarzschild case. Okay, we need to now work out this part in order to get a metric which is also conformally flat, but the coordinates vary in a range whose cluster is compact. Okay, well, I didn't write here at the beginning the coordinate ranges, but I think that you well, actually coordinate ranges will depend on each case. So for example, in this case, it's clear that we have different regions. I should have mentioned this when starting to discuss this case, because, well, we have to consider the regions defined by the following inequalities. Okay. Okay. Because the coordinate system which we have only doesn't cover the union of these three regions. Okay, we at r equal to r minus or r equal to r plus, coordinates break down, and so we need to consider each of these separate each of these regions separately. Okay, so yeah, but this will come in a minute. When doing these transformations, we don't need to worry about this. We don't need to worry about getting the metric written in such a way that coordinates vary in a set whose closure is compact. Okay, so yeah, and so we have to do a further transformation here, which is exactly the same as the transformation which we did with Schwarzschild. Okay, and indeed this transformation always arises when one works with spherically symmetric space-times. Okay, it's just well, I just remind you the transformation here. Okay, so this is the transformation, the usual transformation. Okay, and well, and after doing this transformation, we just get the following form for the Lorentzian part of the metric. You only have to remember the computations of the case of Schwarzschild to get that. Okay, and well, you remember from the previous lecture that now capital T and capital U vary in a set whose closure is compact. Well, just me remember that we did a picture about that set. I'm just going to paste the picture now in here. Okay, so this is the picture. Okay, this is the picture which shows the range in which capital T and capital U vary, which is a range determined by these lines. So the set in which capital T and capital U vary is this square. Okay, just remember from the lecture about Schwarzschild. And now all what we have to do is for each of these regions which we have, okay, we need to identify which part of these regions this boundary set corresponds to, because that will enable us to later draw the Penrose diagram. Okay, well, to do that we need to bear in mind the values of the coordinate capital R when one approaches the boundary points. Well, we computed those values in previous lecture. Those values are written here, and well, just remember that to obtain those values one has to compute the following limits. I'm just remembering things which we did in previous lecture. Okay, so this is because we have the expression of the function capital R here. Okay, so it's just a simple computation to obtain these limits, which we did in the case of Schwarzschild, and that's the result which is written here. Okay, okay, so this is common information which we need, and so what we have to do next is to use this information for each of these regions. Okay. Okay. Well, again, remember that in Schwarzschild we just have 2 regions. Now we have 3, but the procedure is pretty similar. We have to integrate this relation and then study the quadratic behavior of the function which we are going to obtain from the integral. So let me just take this and let us just go down. Okay, so we need to integrate this expression. Okay, So we get the r equal to r squared over minus r squared r minus dr. Okay, right? So well, this is just an integral which we have to do. I'm just going to give you the result of the integral. Well, okay, don't have enough space to have to write the result below. So okay, so this is the result of the integral, which is well, gives r as a function of we give us big R as a function of small r. Okay, right now, yeah. Well, let us just we need to find the quadratic behavior of this function. So we're going to draw its graph, which is also simple to do. Okay. Big R, small r, and well, you can just place r minus, r plus, and well, I don't think I need to explain in detail how to get the graph. We don't need the detailed graph. We actually only know the regions in which the function is increasing and the regions in which the function is decreasing. Okay, and well, you can just read that easily off from the expression which we have. Okay, here this goes to some value called r naught, and yeah, explicit expression of r naught is just r naught is r where big R when small r is equal to 0, and you get that from explicit expression which we have. Sorry, this is this is r plus minus r minus. Okay, right, and so when get the positive quantity, I don't need to put absolute value. Okay, it's clear that it's positive since r plus is greater than r minus, right? Right. So, okay, now we have to consider each of the regions which we have. We have to study separately each of the regions. Okay. Okay. Sorry, here is plus, not minus. Right. So let us take r r greater than r plus. So in this case, we see that just looking at the graph. Sorry, this is what equals to r plus is minus infinite. So if we go back to our picture, we can identify which part of the boundary corresponds to which region in our original space-time. Okay, just don't know what. Maybe I take. Okay, well, I think I can just take again this picture and bring it down. Only got part of. Right, never mind. I just. Okay, get the picture here, and so since r plus, since r going to minus infinite corresponds to small r going to r plus, it means that in this case we have that r equal to minus infinite corresponds to small r equal to r plus. Okay, so I can just now delete this and put it this here. And the same happens with this. Just put this here. Okay, and then big R going to infinite corresponds to small r going to infinite. So I can replace here big R by small r. Okay, can replace here big R by small r. I just okay, this goes here, and okay, so in this region we get this picture. I can just delete what we don't need. Okay, we sorry, don't need this anymore. We don't need this. Well, but we do need to bear in mind that, well, in this case, the conformal factor, well, just go back a bit. You remember, yeah, the final expression. Well, I forgot to mention that one can define conformal factor in the usual fashion. As we always do. Let's put numerator and don't have. Okay. I hope you the denominator is here. Okay. So we have the usual definition of the conformal factor. Okay, well, just move this just to make a bit more of space, right? Right. And so, well, it's also important to consider for each region the sign of the conformal factor, because that will give us the time orientation. Okay, so here in this region we have that the conformal factor is positive, and therefore the time orientation of this region uh, corresponds to the vertical axis, and so I'm just going to draw an arrow to indicate that. Okay, that this is the time orientation. And so, well, after doing that, you can just get rid of the axis because we only know the picture. We only need the picture, this picture. Okay, so you can just okay. Okay, just maybe I should just put the arrow in the center. Okay, right. So this is what we get for for this region, and then the region R minus less than R plus. Well, now well, just look at the graph, and we can compute the limits. Now we have the following result. This is minus infinite. Then plus infinite. Okay, so yeah, again we have to pursue the same procedure. Well, and in this case what we get is that the conformal factor, if you look at the expression of the conformal factor, we get that omega du is negative. Okay, so yeah, well, it's just doing the same thing all again. So I'm just going to give you the result. I don't think I need to repeat the procedure, the explanation again. So that's the picture which we have now. Okay, yeah, and now well, this sign gives us a different time orientation. Okay, well, let me just write this. Okay, this was the previous case, and now we have this case. Okay, and yeah, it's just the same again. Just look at again at this common picture and realize that in this case r equal to infinity is r small r equal to r plus, and big R equal to minus infinite is small r equal to r minus. Okay, right, so that's what we have. And finally, in this case, the last region. Okay, well, again we have a look at the graph, and well, we have that plus infinite, and in this case conformal factor is positive, right? So yeah, in this case we have in this case, well, I'm just going to explain this case with a bit more of detail. Well, this is similar to one the regions of Schwarzschild, but anyway, just to make sure that everything is understood properly, I'm just going to bring this down. Okay. Again. Okay. Sorry about this. I'm just going to. Sometimes it's difficult to get all the items in a given graph. Okay, now so we have right. So in this case, well, we have that big R equal to infinite corresponds to R equal to R minus. Okay, so I can just put here R equal to R minus, and same here, R equal to R minus, right? And the only thing is that here we have to take into account that big R never gets to minus infinity. If we look at the graph here, okay, we see that big R when the small r is positive, big R only gets to R naught, which is some positive quantity. Okay, so as happened in the Schwarzschild case, we need to consider the region such that R naught is equal to RGU, right? Where RGU is what one has in the coordinate transformation, okay? And well, as happened in the Schwarzschild case, you can see that since we have the explicit expression of RT naught, well, it's actually the same as in the Schwarzschild case. We have to just find that to draw the graph of this function in this picture, and what we get is something like this. Okay, and well, as happened in the Schwarzschild case, this region, this graph corresponds to the set of points in which R is equal to 0. Small r is equal to 0. Okay. Okay, just right here. Okay, so in the end, if and since the conformal factor is positive, now the time orientation goes along the vertical axis. So I can just draw a vertical arrow to denote that. Okay, and so yeah, so after all these considerations, you can just delete what we don't need. Okay, and be left only with the part of the picture which we are going to use. Okay. Okay. Okay, right. Okay, so okay, so we have studied the three different regions. Okay, and so we have obtained three different diagrams, right? One diagram for small r greater than r plus, or another diagram for this condition, and now this last diagram, which is for the case in which we have this relation. Okay, so well, this is a bit more complex than in the Schwarzschild case. In the Schwarzschild case, we have two diagrams, here we have 3 diagrams, and so we have now to find out a way of putting all the diagrams together, okay? And we have to do that according to the rules which we explained in previous lecture. Let us do that now. Well, sorry, I forgot to mention something. Well, this is similar to what happens when has in Sparcel. Just remember the transformations. Remember that these transformations leave invariant the form of the metric which we have found, and well, by doing these transformations, we might obtain additional diagrams. Okay, well, it's clear what these transformations do to each of these diagrams. Well, I just delete the axis, but well, I think that somehow the axes are still in your mind. So I think you imagine what happens to each of the diagrams when we apply the transformation, and so it means that we need to add additional diagrams. Okay, well, in this case, for example, t going to minus t doesn't give a new diagram, but this one gives us a new diagram. I'm just going to draw the diagram here. Okay, so take this. It's very simple. We have to swap some labels. Okay. And that's what we get. And here, yeah, well, here is by doing the transformation to minus u. And here, well, we do the transformation yeah, it's the transformation going, so what we get is a new diagram in which now time orientation is changed, so I have to draw the arrow pointing in another direction, and then it's just moving around some labels. Okay, so yeah, and so we get this additional diagram. Okay, well, maybe I should just for clarity add here the label. Okay, right, and yeah, and here again I just need to use well, it's again going to minus u, and then what we get is a diagram which looks like this. Okay, that's going to the time orientation doesn't change, but the diagram does. Okay, so just to draw the arrow here. Here, this label, just to make clear that this goes like this. Okay. So yeah, so that's all the possible independent diagrams which we have, and now it's just a matter of putting all the diagrams together and doing that by following the rules which we explained in previous lecture. Okay, so yeah, let us do that now. Okay. We start with this region. Have to rescale this a bit. Okay. And now we have to add other diagrams along matching sides and keeping the time orientation. Okay. So for example, I can take this diagram. Well, you see that here we don't have the same time orientation. We have to rotate this counterclockwise in order to get a similar time orientation. Well, I'm just going to do that now. Well, to do that I need to move some labels. Okay, so this goes to this side, this goes to this side, this goes to this side, and this goes to this side. Okay. Okay, so we have this, and I have to rotate the arrow too. Now the arrow points in this direction. Sorry. Right. Yeah, so we have this, but well, it doesn't. We don't have matching sides here. Okay. So, okay, so let us just put this diagram aside for a moment, because I cannot join this with any of the... Well, sorry, we do have matching sides. We can just do this. We can just join on that direction. Well, I have to... but first I have to... Sorry about this. This is a bit complicated sometimes. Okay, I have to rescale first the diagram. Okay, and well, we can just join along this direction, but first I need to do a bit of rescaling. Okay, now it's more or less okay, right? So that's what we get. And then, yeah, we need to continue by adding more diagrams. Well, let us just take this other diagram. Well, here we have well, time orientation is already the same, and we have also matching sides here. Let me just put this inside. Okay, so okay, so we can just join along this side. Well, but I have to scale a bit first. Okay, okay, some bit more of scaling. Okay, and then well, okay, so we have now this. Now let's continue. We have just another diagram, which is this one. Well, here we can just join along this side, okay, because we have matching time orientations and matching sides. Okay, so we have to rescale a bit first. A bit more scaling. Okay, and here it is. And then, well, we can just match with the complementary of this diagram. This here can match along this side. Again, I have to rescale first a bit. Okay. Okay. And well, we can still keep adding diagrams. Well, I'm just going to delete first. So just keep the time orientation here. And then here, okay, and then okay, we still have here some more possibilities. Well, for example, yeah, let us okay, that is the easiest way of yeah, for example, this one. Okay, but now, well, we have matching sides, but we don't have matching time orientation, so we have to rotate this in order to get a time orientation. We have to rotate this counterclockwise. Okay, so this label goes here, this label goes here, this label comes here, and this label comes here. Okay, and then okay, I have to rotate the arrow. I have to can just delete this. Okay. And now, well, we can just take this and match on this side. But yeah, have to do a bit of scaling to be able to match properly. Still more scaling. Okay. Okay. Okay, so this is what we have so far, and well, I can delete this part because it doesn't belong to the diagram. And now, well, we can keep adding parts because well, in R equal to infinite, we cannot add anything else because infinite is not a region of the space-time. R equal to 0 corresponds to a coordinate singularity, and so it's not possible to add through a coordinate singularity. Sorry, corresponds to a curvature singularity, so we cannot add through a curvature singularity. But this R plus corresponds to a coordinate singularity, so we can take more diagrams here and keep on adding. But well, it's just that now the way of achieving that is just by taking this picture and putting it, well, I'm just going to move it down a bit because I need to, okay, we can just create another picture similar, and we can just add through this matching part, okay, and so what we get is a diagram, which is, well, we get an infinite diagram here because we can just add also below, okay, and then yeah, we get something which is now infinite actually, okay, and yeah, this is the Penrose diagram of the Reissner Nordström solution, which now is an infinite Penrose diagram. Well, actually, this is the, well, there are two versions. This is the infinite version, but we can also get a finite version if we take the basic building block and do an identification of this part with this part, okay? I cannot do that in 2 dimensions, but you have to imagine this in 3 dimensions, and you get something which, yeah, it's still a Penrose diagram of Reissner Nordström, but it's a different Reissner Nordström. It has a different topology. Okay, I'm just going to write this in this fashion. Okay, well, in the infinite case, okay, we have it's easy to read of the topology. Well, it's u times r times r. Okay, here, well, it's just okay, Okay, but I'm just going to discuss the properties of this, uh, well, of the space-time corresponding to this Penrose diagram. Well, the idea, well, is just what is behind this procedure is the same as what we already discussed in previous lecture. We are doing an extension of our original regions into something bigger, which is represented by this complete picture. Okay, and well, we can discuss the features of this diagram. Um, well, you can see here. Well, this is a bit more complex than the Schwarzschild case. You can see here that there are now infinite Minkowski-like regions. Okay, I'm just going to highlight one of those regions. Well, these are the regions in which R is equal to infinite. Yeah, you see that the diagram here looks pretty much like the Minkowski. So we have an infinite number of asymptotically flat regions. Okay. Well, I could use the terminology which one normally uses in Minkowski and call this future null infinity and past null infinity rather than R equal to infinite. So that's what we have here. Okay. And well, I'm just going to use the notation 1 for these asymptotically flat regions. Okay. And then, well, if we just draw a causal curve, which we can do because, well, as we know, it's easy to draw in Penrose diagrams causal curves. We see that if we have an observer which starts in any of the asymptotically flat regions and it leaves the asymptotically flat regions through R plus, he cannot come back to this any of the asymptotically flat regions. So R plus will correspond to an event horizon. Okay. And yeah, well, you see, since this pattern is repeated itself, this happens if we work in any of the asymptotically flat regions. Okay, so okay, well, I can just add the labels in all the asymptotically flat regions. Okay. Okay, so we have asymptotically flat regions and we have an event horizon which isolates the asymptotically flat regions. Okay, right, but we have something else. We have another horizon because when an observer gets in leaves any of the asymptotically flat regions, he enters into some different region, but this region doesn't contain any singularity. And in fact, there is another horizon here, which separates this intermediate region from the region in which the singularity is present. Okay, and this intermediate region is separated by an horizon, which is the region r equal to r minus, and the name of this horizon is Cauchy horizon. Okay, and why is this called Cauchy horizon? Well, I'm just going to explain that in a second, but let me just first tidy up this draw a bit first. So we have this intermediate region. Okay, I'm just deleting stuff which we no longer need. Okay, so this was R plus, R plus, R plus, R plus, and this is the Cauchy horizon. Okay, okay, yes, minus minus here say r minus r minus this r equal to 0. Okay, and why I'm calling this Cauchy horizon? Well, the reason is that, well, this the union of all these four regions gives us a globally hyperbolic subset of, because, well, we can just, I'm just going to draw a Cauchy hypersurface here. Okay, you can see from the diagram that sigma is a Cauchy hypersurface. That is a Cauchy hypersurface for the set formed by the union of 1, 1, 2, and 2. Okay, because this is set is globally hyperbolic. Okay, sorry. Okay, the whole space-time is not globally hyperbolic. We will see in a minute why, but this subset is globally hyperbolic, and the boundary of a globally hyperbolic set is called Cauchy horizon. Here, this boundary, as we can see in the diagram, is represented by r minus here up here and r minus down here. Well, just remember that this the infinite is not a region, so we cannot. It's not a region of the space-time itself. It's the region of a conformal extension, but not a region of the space-time itself. So we cannot speak of this as a subset of the space-time. But r minus and r minus and r plus are regions of the space-time. Okay. So observer which enters the region 2 and lives through the Cauchy horizon and sees himself in something in a region which we will call region 3, which contains a singularity. But unlike in the Schwarzschild case, singularity is now a time-like set. Okay, so it means that the observer can avoid the singularity. But since the singularity is time-like, it means that information can be created at the singularity, and it can get through. It can get to other sets of the space-time. Okay, so what this means is that region 3 is not going to be globally hyperbolic. I mean, because we cannot draw a Cauchy hypersurface in this region, okay? So that's why the complete space-time is not globally hyperbolic, but we can find subsets which are globally hyperbolic, okay? And yeah, indeed, for example, if we just concentrate in any of the regions 1, they are globally hyperbolic themselves. So for those regions, the event horizon is a Cauchy horizon too. But well, we call them event horizon because they isolate the asymptotically, they separate the asymptotically flat region from the other parts. So indeed, we can speak about a black hole solution because we have an asymptotically flat part, which is like Minkowski, and we have an event horizon, which separates the asymptotically flat part from something else. Okay. So this represents still a black hole solution. If we get back to our observer, we can notice an interesting feature. So the observer starts in one of the asymptotically flat regions, enters the intermediate region, enters the region which contains the singularity, and since the singularity is time-like, he can avoid the singularity, he can continue and, well, enter in any intermediate region which is different from the previous one, and then he ends up in another asymptotically flat space-time. So he starts by entering the black hole. The observer can exit the black hole, but when he exits, he ends up in another universe, in another asymptotically flat region, which might represent, for example, another universe. Okay, and well, if we just look at the other diagram, which we obtain by doing the identification, well, the only thing is that, well, well, we can just, well, in this case, well, this is region 1, this is region 1, this is region 2, and well, this is let us just call the region which contains the singularity region. Well, yeah, I have to return region 3. Okay, so this is region 3. Okay, so an observer can start at in region 1, enter the black hole. Well, here we are following a different time convention, but it doesn't matter. So then the observer continues through a region in which the singularity is. Then he can enters another intermediate region, and then when he comes here, given that the identification, it means that he ends up here. So in this picture, the observer enters the black hole and then leaves the black hole at the same universe in which he entered, but at a different time. So we can think of this representation as a time machine. Because there are closed time-like curves here. And this observer is just an an example of this, one of these closed time-like curves. Well, I would have to join this. Given that we have an identification, then this curve, this time-like curve, is indeed a closed time-like curve. And well, because, well, actually, this curve follows the S1 of the topology. Okay, so this is indeed a time machine. We could think of this extension of the Reissner Nordström black hole as a time machine. Okay. Well, it's not, of course, it's not clear that how to build such a device in reality. Well, this is indeed an illustration of the fact that the metric doesn't determine the topology, because, well, we have two. Well, just see here that we have two different diagrams which we obtain from the same metric, and they indeed represent spacetimes with different topologies. Okay, so that's what we have. They are completely different, and we have obtained this from the metric by means of a very simple procedure, and we didn't have to do any explicit computation, because all this is, well, as always with Penrose diagrams, they don't give you a formal proof, but they give you a very valuable information which you can later work out by means of formal proofs. And in fact, it's possible to obtain the explicit extensions, what, at least in this case, one can work out the extension and obtain a coordinate representation of this space-time. And well, this is not easy. This is highly complicated. This is not straightforward at all. Okay. Okay, so this concludes our discussion of the, because, well, just remember that we were discussing one case of the Reissner Nordström solution, the case in which we have two different roots. And now let us discuss the case in which one has two different, when one has just one root. Remember, we have this case in which one has one root. And this is the so-called extremal case. Okay. Okay, so let us discuss the extremal case now. Remember the line element of the extremal case? Okay. Well, in this case, the coordinates are valid in two separate regions. Okay, so we see that the region which we have before now it's not present, and so what due to this fact, what happens in the Penrose diagram is that the diagram which corresponded to this region is gone also. I'm not going to do the full details of the Penrose diagram because the procedure is pretty much the same as in the previous case. I'm just going to indicate the result. You can work out yourselves the details as an exercise. And so in this case, we have two independent Penrose diagrams due to the fact that we have two separate regions covered by the coordinates. Okay, let me just show you the independent Penrose diagrams. This is one of them. Sorry, just have to put it again. Okay, so this diagram corresponds to the region in which R is greater than M, and well, we can check the conformal factor, which one gets in the conformal representation is positive, so this is the time orientation, and then we have another independent Penrose diagram, which is here, right? Okay, and yeah, so it corresponds to the other region, and I have indicated here the location of R equals 0, which is still curvature singularity. Okay, and so all what remains to be done is to match these two Penrose diagrams and put them together in the fashion which we already know. Okay, so this is all very simple. Just give you, essentially we get a diagram which is similar to the diagram of the non-extremal case, but with one of the regions missing. You will see in a minute. I have to rescale this because otherwise the diagram doesn't fit in the screen. Okay, so this is one part, and then we start matching other parts. Along matching side as always. Okay. Okay. And now we have just to repeat this pattern. Okay, just I can match this side. And this is repeated indefinitely. Right? Okay. Okay. Well, let me just remark that if we do the transformation to these two diagrams, then we get another couple of diagrams which are reflections along the vertical axis of these two, and then that gives a Penrose diagram which is identical to this one, but reflected with respect to the vertical axis, but the properties are the same. Okay. Well, I would only like to mention here that we no longer have a Cauchy horizon. Okay, now here R equal to M corresponds to a event horizon. Well, and well, this is clear from this diagram if you remember the considerations which we did in the non-extremal case, okay? So we still have a number of regions which represent asymptotically flat ends, and we still have regions which contain a time-like singularity, which represent a black hole. So this is still a black hole, but no Cauchy horizon as we had before. Okay, and again, singularity can be avoided. An observer gets into the black hole region and then leaves can leave the black hole region and end up in another universe. Okay. Right. Okay. So I think I don't need to give further explanations. And what I would like to mention is that, as happened before, we could get another diagram which represents an extension with different topology. Well, here the topology is the same as in the non-extremal case. And well, if we just take the two independent diagrams, well, we just can do it here. Okay. Okay, so this was one of the diagrams, and this is another diagram, and so we can just join in this fashion. Okay, so we get the basic pattern which we had before, but now rather than putting together these two pictures indefinitely, we can just do an identification and then identify this side with this side. Okay. And by doing this, what we get is the diagram of another spacetime which has a different topology. Okay, and in this case, well, again, this is an example of the fact that the metric doesn't determine the global topology, and in this case, this spacetime has closed time-like curves. This is the same as what we had in the non-extremal case. Okay, so well, just okay, I'm just drawing a closed time-like curve. This is an observer which gets into the black hole region, and then since this is identified with this, then the observer exits at an universe which is the same universe in which he started. Okay, so you again can think of this as a time machine. Okay. There isn't much to say about this diagram, which we haven't said before. And so let us finish with the discussion of the case with no horizons. Well, it was when, well, this is the case in which we have this condition. Okay, and let us just define a new parameter. So the metric in terms of this new parameter is written in the form okay. Just remember the three cases which we presented at the beginning of the lecture, right? So, okay, again, the procedure to get the Penrose diagram of this space-time is similar to the other cases. So just take Lorentzian part and do a number of appropriate coordinate transformations. Okay. I'm just going to write the formula. I don't think I need to tell you what I am doing because this was explained before. Okay. And then always this gets transformed into the usual form. With the usual transformation. Okay, so now the thing reduces to studying the relation between to integrating this relation. Well, you need to just do this integral, right? And then this gives you the relation between big R and small r. Okay. Right. So, well, you can just draw a picture of this function. Okay. This is always the same story. This R, and well, you can see that this function is always increasing, and it has no singularities when R is positive. So its qualitative behavior is like this, something here, which is R naught. Okay. R naught, which is a positive quantity, because by construction this is a positive function. Okay. Right. So it's simple to check that from the graph. Just from the graph we get the okay. So if we just remember our usual picture, which I'm putting here, okay. Well, then we deduce that r equal to infinite corresponds to small r equal to infinite rule. So this is the infinite region. And big R never gets to R. Big R never gets to minus infinite, as we can see in this graph when R is positive. And so again, we have to study the set in which R naught is equal to R as a function of du. Okay, and this we have the explicit form of this function. Well, it's always the same. When has that by doing when does this coordinate transformation, is exactly the same form as one uses in the all other cases. So we again get something. The graph of this set is the blue line which I am going to draw here. Okay. So in this case we only have an independent diagram. Well, of course we can do the usual reflection. I'm not going to. That doesn't give us a diagram which we can use to join. So in this case, only an independent Penrose diagram is present, and so the Penrose diagram is quite simple actually. Okay. Okay, so we have, well, I can actually delete this because it doesn't belong to the region of interest, and so we get something very simple. Okay. Okay, and well, so it means that the coordinates which we were using for our metric in this case actually constitute the complete extension. There's no way of adding more diagram, adding a copy of this diagram here, because this is a curvature singularity and we cannot extend through an infinite region. Okay, so well, the most important feature of this diagram is that it contains an edge singularity. Why do I say that we have an edge singularity? Well, the reason why I'm saying that is that an information coming from the singularity can reach the far region, because, well, this is still asymptotically flat, because you see that this part of the diagram looks pretty much like Minkowski, so we can say that this is asymptotically flat, but now the region which contains the singularity is not separated from the region, from the asymptotically flat region, by an event horizon. There is no event horizon here, so it means that if a particle is created at the singularity, then the particle can travel all the way to the infinite region. Okay, so that's why I'm saying that it's an edge singularity. The singularity can be observed in the far region. Okay. An important question is whether edge singularities do exist in the nature. And, well, the answer is not known. And actually, well, there is the so-called cosmic censorship, which tells us that an edge singularity cannot be developed in a real physical process. Okay, this is a very rough formulation of this. Okay. Okay, so this concludes our discussion of the Penrose diagrams and global causal structure of the Reissner Nordström solution. Thank you for your attention.